Hi everybody, my name is Nerla. I'm a PhD student at University of Illinois Urbana-Champaign, hopefully in my last year of my PhD. And today, I'll be talking about upgradable TEs. So what is a trusted execution environment? The way I like to think about it is like it's an isolated memory region of your CPU, and it's encrypted with this secret key that's embedded inside of the CPU such that no other process can use that decryption key. And it gives you these hardware-based guarantees of privacy and integrity for anything that is running inside of the TE. So the way that we verify these guarantees is through a process called remote attestation. And what this gives you is like a proof that you can send to a different party, and they can have some assurances that you are running the correct thing in a real TE. So if we take a closer look on what remote attestation is and how it works, typically what would happen is that you have your TE application, and it would output something called a remote attestation report. So inside of that report, they have something called a code hash or MR enclave if you're thinking about Intel SGX. And what this code hash is, it's a hash of the entire memory that was loaded into that TE. So it's kind of like a description of the code running inside of the TE. And in addition to this code hash, the report would have a public key that was generated inside of the isolated memory region of the TE. So only the TE can use that decryption, the key that is in that report. And so what a user would usually do, they would go on your GitHub page and look at the code that's supposed to be running the TE and make sure that it's not arbitrarily like leaking their data. And once they have like audited that code, they would rebuild it and regenerate this code hash. And then they can look at the report and see that these two code hashes match. And then what they would do is take the public key in the same report and encrypt it. And so now what has happened is that only the TE can decrypt this encrypted data. So what do I actually mean by upgradability of TEs? So essentially it's just good software practices, like you want to be able to patch vulnerabilities that you find in your code, you want to be able to add new features to your TE, but like how do we do this securely? So we've kind of like identified 3 different areas that we can improve the upgradability of TE applications. So the first one is like looking at the remote attestation process. It all depends on this code hash. So if you think about if you wanted to upgrade your TE code, the code hash would be completely different. So you'd have to like keep a copy of your private data and redo the remote attestation and re-encrypt your private data with any little change you want to make to your TE application, and that's like pretty cumbersome to do. The second area is kind of thinking about security vulnerabilities of TEs. So if it comes out that there's a bug in Intel SGX, we have to be able to like respond to that and like minimize the damage that that bug could potentially cause. And the last area is thinking about like what it means to have an upgrade to decide to do an upgrade of a TE process in a decentralized manner. So this would typically be like a DAO would decide to change the code of your TE. So we want to think about, okay, what if the DAO is malicious? What if they are upgrading to a version that's arbitrarily going to leak your data? Like how do you protect the users during this upgrade process and this decision-making process? So first, I'll just talk about the ideas of seamless code upgrades. So the basic way you would do this without doing remote attestation again is you would bake into the version 1 of your TE that it is allowed to upgrade if it has the authority from the user. So the user would provide the code hash of the new version that they agree with, and then the TE would automatically transfer it to the new version for you. But the problem in this kind of setup is that a bug in the version 1 that doesn't let you do this upgrade could mean that you actually lose your data during this upgrade process. And this is like really bad because the whole reason we want to do upgrades is to fix bugs. So it's kind of like a circular problem. And if we think about what it would mean to do this for a decentralized audience, it would typically be like a DAO voting on chain, and then you'd use a light client to check that the vote passes. And we already know, if you ever worked with light clients, it's like really hard to get them completely correct and not have any bugs in the light client implementations. So this is kind of where we get this idea of we need MPC for TEs. So what we want to do is have this original plan that I just presented as the main the way we would upgrade the TE code, but we want to have a backup that we can activate if there's some kind of bug in this upgrade process. So this would basically use this, what is called the MR signer method of encrypting data. So before we were thinking about MR enclave, which depends on the code hash, but now we want to depend on a developer signature. So we would basically distribute this MR signer key among the MPC members or like the DAO voters or the security council, and only they would be allowed to activate this backup. And so the way we kind of minimize the chance of bugs in this process is that we don't force the Ts to do a check of some on-chain votes. And so that kind of opens us up to like a potential malicious MPC network with which can like activate this backup without doing anything on-chain. And we wouldn't know that this happened. So the way we kind of protect against this is to have some kind of evidence that is produced that this backup mechanism hasn't been used to kind of maliciously upgrade the TE. So we have a counter value that counts how many times the key was used, and we can post on chain some evidence of the key has not been used to do a malicious backup. And if it has been used, or maybe they didn't provide the evidence, then we can implement some kind of punishments like slashing. Okay, next I'll just quickly go over like the idea of security upgrades. So Ts are like kind of notoriously known for having these kind of bugs that come out. So like that's one of the main reasons people don't want to use them. And this is kind of like a fundamental problem for Ts because all of the guarantees depend on your hardware implementation being correct. So if it's not correct, then you kind of lose your guarantees. And this is like very fundamental problem because yeah, it's based on the implementation, which can always have bugs. So how do we like anticipate this and protect against these vulnerabilities? So this is like the timeline of what it would look like for if a vulnerability is announced. I won't go over the whole thing, but I'll just like point to this part of it, which I care about. It's the time period in between when the vulnerability is found and announced, and between when that is announced and when a patch for the vulnerability is released. So like what can we do in this time period to like reject the nodes that we know are vulnerable and make sure they don't leak our data? So the basic idea of how we would do this is we have a security version number that is hard-coded in our TE application, and any data that comes into the TE has a security version number that is like allowed to decrypt that data. So if the T like does a check and sees that, hey, this data has a higher security version number, it would not ever touch that data. It wouldn't decrypt it, so that data wouldn't be subject to the vulnerability. But there's still like problems with this because what if the data is like old, it has an old security version number? If you think of the data coming in through a blockchain, like you can always get an old block that has an old number and like trick the T into like leaking that old data. And I'll just say like this, the way that this would happen, the way that we think about like the T running is like it's continuously like processing blocks. And so it would always have like the latest security version number as long as it's like up to date with the chain. But you know, if the T restarts, it doesn't know what happened in the last X amount of blocks. Maybe the security version number got updated. So then we come out with this concept of secure restart, where we want the TE to have the latest view of the blockchain. So the way we do that is we generate a random challenge in the TE to where basically this random number has to appear on chain, and then we know that that block was actually produced after we created this random number. So it's like ensuring the freshness of the security version number for a TE that restarted. And there's still more problems with this, obviously, because if we're thinking about we want to protect against a vulnerability, like what if the vulnerability allows a TE to like completely bypass all of these checks? So the one thing that we kind of can see from the protocol of secure restart is it doesn't rely on the privacy of the TE memory. So even if the vulnerability is about leaking the privacy of the memory, we can still rely on the secure restart. But it does depend on some other stuff, such as this randomness generation. So this random number is generated using the RDRAND instruction. So if that randomness can be biased, then we can get around this. And another way that it could go wrong is if the vulnerability is about code injection. So if we can just inject some kind of jump past the security version number check, then that would also bypass our checks. And I won't go into like the low-level details of why we think this, but the idea that we're kind of toying around with the secure restart is that the secure restart functionality would basically be secure as long as the vulnerability that has been announced has a patch that can be applied to it. So if there's no patch that we can apply to the hardware, that essentially means you have to throw away the whole machine because it's going to be vulnerable for the end of time. So essentially what we're trying to argue is that these unpatchable vulnerabilities are like way more rare than a patchable vulnerability. The last thing I'll like touch on is this concept of decentralized upgrades. So upgrade governance, so how do you decide to actually do an upgrade in the first place? So when we're thinking about TE applications, we typically think like, okay, there's one user that's going to just decide to do the upgrade, but in reality, it's gonna be like some kind of DAO that votes on doing the upgrade, and we may not trust the DAO completely. So we wanna be able to like, if we disagree with the DAO's decisions, protect ourselves from kind of this malicious majority. So we're kind of thinking about these opt-in versus opt-out mechanisms that we can implement with the TEs. There's still some like ongoing research, but I'll just say that essentially what we want to do is to kind of enforce the ability to opt out inside of the version 1 of the TE, and that would like prevent the malicious majority from updating if the user had opted out. So we can do this for both privacy and potentially integrity violations that could happen in this upgrade process. I guess I'll just go to my conclusions. This is kind of just summarizing everything that I've talked about. Like first, these benign code upgrades where you just want to like apply some kind of new features or stuff to RTE. Security upgrades where we're patching vulnerabilities. And lastly, like this, even deciding how to do an upgrade and how we can like keep the user involved and keep them like, keep their agency in the process. So yeah, thanks.